Gases are mostly invisible, but they're all around us. When we talk about gases, we mostly talk about four properties of them, which is pressure, volume, temperature, and the amount of gas in moles. So when we talk about the pressure of a gas, it's mostly due to the collision of all the little gas molecules that are just bouncing off their container that they're stored in, no matter what it is. So as we change other aspects of it, like if we increase the temperature, all the molecules move faster, and then they bounce off the walls even harder, and then of course the pressure goes up. So that's how pressure works. And all of them are related: pressure, volume, temperature, and amount. The SI unit for pressure is this Pascal thing. It's a kilogram per meter second squared, but we don't really use that too much in chemistry class just because it's not really applicable to what we need to talk about. So we use other units. It's important to note the gases are compressible. You can squeeze them into a smaller volume by increasing the pressure. So all of them, again, are related: the pressure, the volume, the temperature, and the amount. So other units that we use besides the Pascal would be an atmosphere. One atmosphere is, like 101 kilopascals, and we also use millimeters of mercury. So 760 millimeters of mercury equals 1 atmosphere. And most of the time, our problems that we do are going to be in millimeters of mercury or atmospheres. That's it. We really don't use bars too much, pascals too much. I will give you all of these definitions of the relationships on an exam, just so that you can do the conversions between them if you need to. But for the most part, we'll always either be using ATMs or millimeters of mercury, nothing else. So again, temperature, pressure, volume, and the moles are all related. And if you hold any two of them constant, you can show a relationship between the other two, which is really useful for doing problems. Okay, and those are called the empirical gas laws. And I won't expect you to know them by name. Like, I won't expect you to know which one's Boyle's law and which one's Charles's law and things like that, but I will expect you to know the actual relationships. So Boyle's law is about volume and pressure. And it says that if you double the pressure, the volume goes in half, which makes sense. So if you double the volume, then the pressure is in half, right? Because if you give a gas more space, you double the volume, then it obviously is hitting the walls less than it was before. So these vary inversely, okay? As long as you keep temperature the same, and as long as you don't add any more moles of gas, they're the same. So you can say movime and pressure are inversely proportional. And if you look at this picture, you can kind of see this. We have a 1.40 liter container here, and it's at half of an ATM. But if we compress it down to half the volume, right, 0.7 liters, we get double the pressure, 1.0 ATMs. It's really intuitive if you kind of think of it that way. So if you compress something to half the volume, you get double the pressure. And conversely, if you were to increase that to twice the volume, you would get half the pressure. And that makes sense. So we can use these to make a relationship between volume and pressure. And we can say that P times V is a constant. And therefore, we can use P1V1 equals P2V2, or I and F, initial and final, or however you want to say that. But we can do problems like that. So let's look at a problem. A sample of oxygen gas. Okay, so we have 38.7 milliliters at 751 millimeters of mercury and 21 degrees Celsius. So if our temperature remains constant, we want to calculate the new volume. So if we take situation 1 to be 38.7 milliliters and 751 millimeters of mercury, and then situation 2 to be 359 millimeters of mercury. Okay, so we want to know what the new volume is going to be. Let's see if I can make that. Okay, so we have P1 V1 equals P2 V2. So we have these both in millimeters of mercury, so that's okay. We can keep them together. And we have milliliters on one side, so we'll just get milliliters on the next side. Now, if we think about this, we want to know what's going to happen to it. We're roughly making this half the pressure here, right? So we expect the volume to go up, I think, right? Wouldn't you think? So if we do P1V1, so we'll do 751 millimeters of mercury times 38.7 milliliters equals 359 millimeters of mercury times V2. And we solve for V2. We're going to get an answer, let's see, 81 milliliters, 81.0 milliliters. Okay, so does that make sense? We went from 38.7 milliliters to 81 milliliters. I think that makes sense because we expected it to go up because we're cutting the pressure in half, or almost in half. So that makes sense, I think. All right. So we have Charles's law now, and Charles's law relates temperature and volume. So we can do the same sort of thing. The volume, if we leave the pressure the same, is directly proportional to the absolute temperature. So if we double the temperature, the volume doubles. That makes sense. All right, so what they're doing here is they're putting a balloon into liquid nitrogen. And what does that do to it? You put the whole balloon in there, and it makes the air inside, the temperature goes way down, so the volume goes way down. And then as it warms back up to room temperature, the balloon expands back to its original size. And if you click on this link when you're going through the slides, it's a really cute, demonstration of this by some folks at MIT, and it has balloon animals and all, and it's really, really cute. So go ahead and watch that when you get a chance. So if we look at Charles's law in these little pictures, we have 100 K, which is Kelvin, 100 Kelvin, and we have 1 ATM, and we have 0.26 liters. So if we double the temperature to 200 K and we leave it at 1 ATM, we are now increasing the volume, right? So we have volume is expanding to 0.52 liters to keep it at the same pressure. Because if we didn't keep it at the same pressure and we just kept it the same volume, then we would have a much different thing happening. With the temperature going way up, our pressure would go way up too. Okay, so we have volume is proportional to temperature, and that way we have our V over T is a constant, and we can do our problems like this. V1 over T1 equals V2 over T2. So here's an example. A balloon at 20 degrees C occupies a volume of 346 milliliters. So if we place it in the freezer at negative 40 degrees C, what's going to happen? So our situation 1 is 20 degrees C and 346 milliliters. Our situation 2 is going to be negative 40 degrees C, and we need to know the new volume. So we want to say the question is volume 2. Now, notice that these are both in degrees Celsius, except that when we talk about gas temperatures, we always have to put it into Kelvin. So this is going to become 293 Kelvin, and this is going to become 253 Kelvin, right? Wait, 270 minus 40, that's 233 Kelvin, sorry. Okay, so we have to put this in our equation. So we're given V1, T1, T2. And here's what it looks like. 346 milliliters over 293 Kelvin. And then we have to put in our V2 or VF or whatever you want to call it over 233 Kelvin. And you solve, you cross multiply to solve this, and you get 276 milliliters. So does that make sense? If we're going from 20 degrees C to negative 40, our temperature is going down. So we would expect our volume to go down as well from 346 milliliters to 276. That makes sense. Okay, so now if we combine all these gas laws, we get a whole thing here. Volume is inversely proportional to pressure, but directly proportional to temperature. So we can combine these, and we we'll get P1V1 over T1 equals P2V2 over T2. So let's see how this works in a problem. Okay, so we have nitrogen gas. The volume of the gas produced, we'll say this is situation 1, is 10.1 milliliters. We have 23 degrees C, and we have 746 millimeters of mercury. That's the pressure. Okay, so situation 2, what would be the volume of the gas? So we're looking for V2 at 760 millimeters of mercury and 0 degrees C. Okay, so we're going to put this into our equation that we just learned. P1 V1 over T1 equals P2 V2 over T2. Okay, so we're going to put this into our equation, and we're going to make sure to convert these 2 degrees Celsius temperatures to Kelvin. 296 Kelvin, and this is, of course, 273 Kelvin. All right, and we solve for V2, and we get 9.14 milliliters. 9.14 milliliters. So this makes sense. 9.14 milliliters. So it didn't go down that much because we had 10.1 milliliters before. Because we changed the temperature, but at the same time we changed the pressure. So we're doing different things there. All right, so the only thing we haven't addressed yet is to increase the moles of gas. If we leave the temperature and pressure the same, what happens if we add more gas? So if you look at this picture, we have a cylinder, and we're adding more moles of gas. So obviously if we add more moles of gas, it's going to increase the pressure because we have more molecules that are hitting the walls at different things. So in order to return it to the original pressure and keep the pressure the same, we have to increase the volume. So that makes sense. If we're going to add more gas in order to keep the temperature and the pressure the same, we need to add more volume. Okay, so the volume is proportional to the moles of gas. All right, so one thing that we have to say about gases is that there is a standard temperature and pressure. And this is something that we're going to refer to all the time. So standard temperature and pressure, which is called STP for short, is always 0 degrees C and 1 atm. And one thing that's really important to note is that at standard temperature and pressure, 1 mole of any gas is always going to have the same volume. 1 mole of any gas is going to be 22.4 liters. So they call this Avogadro's gas law because Avogadro a long time ago said, well, hey, I think that if you put 6.022 times 10 to the 23rd molecules of any kind of gas, whether it's a monoatomic gas or a diatomic gas, it doesn't matter how many atoms are in the gas, or if it's a CO2 or like a molecule methane, but that number of particles of any gas is always going to have the same volume. So that's why it's at standard temperature and pressure. We just define that as 1 mole of any gas is always going to be 22.4 liters. And you can use this to figure a lot of things out. So you should know that 22.4 liters is the molar volume, and that's for 1 mole of gas. But you won't necessarily need to know it for every problem. But it'll be really useful if you remember it. It'll help you solve a lot of different kinds of problems. Okay, so the ideal gas law, when we combine all of these things together, is called PV equals nRT. So we have our pressure and our volume there. N is the number of moles. T is the temperature, obviously, in Kelvin. So what in the world is this R? This R is a gas constant, okay? And this constant is given to you, not that you won't remember it by the time you finish with a million of these problems, but we usually use the value of R as 0.08258 liter atmosphere per mole Kelvin. So 0.08258. And we're always going to have liter atmosphere per mole Kelvin. You have to make sure that when you're doing this, when you're using PV equals nRT, that your units all cancel out. So if your temperature is not in Kelvin, then this Kelvin is not going to cancel out. If your pressure is not in ATMs, then that's not going to work. You're going to have to convert it. If your volume is not in liters, you're going to run into problems, and your N is always going to be in moles. So this is something that we use all the time. If you're using PV equals nRT, and you're using this value of R, you need to make sure that you're using liters, atmospheres, moles, and Kelvin all the time. Okay, so let's see how a problem works. How many moles of carbon dioxide, CO2, are there in a 50-liter gas cylinder at 21 degrees C if the pressure in the cylinder is 15.7 atms? Okay, so we have CO2. Now, we have 50.0 liters. This is V, obviously. We have 21 degrees C. This is T, but we need this in Kelvin, remember. So we go 273 plus 21, and we get 294. Whoops, I'm like moving my screen. 294 Kelvin. Okay, and we have pressure is 15.7 atms. This is P. So we don't know N. Okay, so we have our equation PV equals nRT. We're just going to solve for N. So we can say N equals PV over RT. Does that make sense if you just divide both sides by RT? And we can stick everything into the equation. Okay, 15.7 atms and 50.0 liters over R, 0.082058 liter atmosphere per mole Kelvin. And here's our T, 294 Kelvin. So let's make sure that all of our units cancel. Here's our ATMs. There's our liters. Here's our kelvins. So we're left with moles in the denominator. So it's the denominator of the denominator, so it's going to go up there. And we're going to end up with just moles. So that makes sense. In this problem on the slide, they don't rearrange for N first. I like to do that because it makes it very easy. But you can certainly put it into the equation and then solve it later. You end up with N equals 32.5 moles. 32.5 moles. And this is a fairly straightforward problem. So you just put everything into PV equals nRT, and you should end up with the right answer. As long as your units cancel out, you're not going to end up with a problem. When your units don't cancel, then you'll end up with a problem. Okay, so let's do a sample problem from the worksheet. Let's do number 4. A gas in a 3.00 liter vessel at 22 degrees C. This one we're going to do right here that I'm highlighting. Okay, so I'll keep this highlighted. And the way we have to set this up, we need to figure out which law to use. So we have situation 1, and we know that it's 3.00 liters. This is V. And we have 22 degrees C, right, which is 298 Kelvin, and this is temperature. And then we have 1.75 atms, and this is pressure. Okay, so we have a P, a T, and a V. And then we have situation 2. Let me write it down here. So we have 0.986 liters. This is volume. We're going to call this volume 2. Then we have 35 degrees C, which is 308 Kelvin. This is temperature. So it wants to know what the final pressure is. So we're solving for P2. Okay, that doesn't, no, I didn't mean to say R. I wonder if I can erase that. No. So anyway, just it's P2. Okay. So we need to use our combined law. P1 V1 over T1 equals P2 times V2 over T2. We need to put all of these variables in here and then solve for P2. Okay, so I'm going to clear this screen, if I can figure out how to clear it actually. I think I have to move it. Oh, there we go. Actually, I don't have to clear it because I can just move it over. So we have 1.75. This is ATMs. Times 3.00 liters over 295 Kelvin. equals P2, this is P2, times 0.986, which is liters, over 308 Kelvin. Okay, we do some algebra, cross multiply, solve for P2. We get 5.56 ATMs. So we can tell which law to use if we just make a list of everything we have in situation 1 and everything we have in situation 2 and see what we have changing and what we don't have changing. If we had the temperature not changing, then we would just be using P1V1 equals P2V2. If we had the volume not changing, we'd be able to do pressure over temperature. So, you know, it doesn't really make a difference what variables you have as long as you can tell which ones are changing and which ones are not. Okay, so let's do another problem. Let's see if I can make this smaller. Okay, let's do number 5 now. A bicycle tire with an internal volume of 1.52 liters, 1.52 liters, this is V, contains 0.406 moles of air. 0.406 moles, and this is N. The tire will burst if its internal pressure reaches 7.25 ATMs. 7.25 ATMs. So this is pressure. To what temperature in degrees Celsius does the air in the tire need to be heated to cause a blowout? So we're looking for T. Now remember T, we're going to find this in kelvins, and then we're going to have to convert to Celsius. Okay, so let's use our PV equals nRT equation. We'll solve for T. So T equals PV over nR. And we're just going to put everything into the equation. So we have 7.25 ATMs times our 1.52 liters. N is 0.406 moles. And then our R is 0.08258 liter atmosphere per mole Kelvin. Okay, so let's just make sure that everything cancels. Our ATMs cancel, our liters cancel, our moles cancel, and we're left with Kelvin. Okay, so we have temperature equals 330.9. And then when we convert that to Celsius, we get 57.8 degrees Celsius. Okay, so this is a standard PV equals nRT problem. It's really just plugging in the numbers wherever you have the variables and making sure that all your units cancel. So there's not a whole lot more to it. So the other thing we can do with PV equals nRT is we can use it to calculate the molar mass or the density of a gas. Okay, so we are going to use our ideal gas law, PV equals nRT, to calculate this because the N equals the number of moles, and we know that we can convert that to mass without any sort of problem. And so we end up with density, if we just rearrange the equation, which is just grams per liter, or we can calculate molar mass, which is grams per mole. Okay, so it's pretty straightforward, but we have rearranged these equations into this extra format for you to use if you want to do a problem. So if we want to figure this out, what's the density of methane gas at 125 C and 3.50 ATMs? So we're going to write our molar mass down. We have our pressure, 3.50 ATMs. We have our temperature, and we just put it into this density equals molar mass times pressure over RT. It's really not that difficult. You could also do it without having the density and the molar mass if you just realize the density is grams per liter and you just use molar mass to convert. But you have this equation. I will provide it to you on the test so you can use it if you need to. So we're just going to plug and chug, put the density, the molar mass, the pressure in there. And here is how everything works out. We have density 16.04 grams per mole times the pressure over our R, and then 398 Kelvin. So we have everything canceling, and we end up with density in grams per liter, and we have 1.72 grams per liter. So that's a pretty standard way to do it. Let's see if we have another practice problem here. All right, so here's a practice problem. Find the density of hydrogen sulfide gas at STP in grams per liter. Okay, so there's two ways to do this, but we're going to do, the way that we just went over first. We're going to say density equals molar mass times the pressure over RT. Okay, so we have our density. We know that at STP, we have pressure is 1 atm, right? Because we remember that from the definition of STP. And our temperature is 0 degrees C, which is 273 Kelvin, right? And we know our molar mass of H2S gas is going to be 34.09 grams per mole. Okay, so now we just put everything in here. So our molar mass, 34.09 grams per mole, times our pressure, 1 atm, over 0.082058 liter atmosphere per mole Kelvin, times our temperature, which is 273 Kelvin. That's a 7. Okay, so let's make sure that everything cancels. We have our ATMs canceling. We have our Kelvins canceling. Why is it doing that to me? We have our moles canceling, and we end up with grams per liter right here. Okay, so when we put all of this in, we end up with 1.52 grams per liter hydrogen sulfide gas. The other way we could have done it, which is a lot easier, is if we just remember our molar volume. 1 mole of any gas at STP, 1 mole of any gas at STP is 22.4 liters, right? So we know the molar mass, that's 34.09 grams per mole. And if we just do density equals 34.09 grams per mole divided by 22.4 liters, we get 1.52 grams per liter, because remember we have times 1 mole here, right? We're only doing 1 mole. So we have grams per liter. So that's a much easier way to get to the same answer, but I would recommend doing it this way because you don't have to remember this little shortcut, and then you don't have to remember the equation either, because this density equation is given to you up here. We're going to give you this density equation on the test. Okay, so that's another way to do it.